A very good day. My name is DARSHAN and these are my teammates, FARIS, WONG and MOIRA. So today we'll be doing lab 2, which is a radial heat conduction experiment.
Assalamualaikum, saya Faris akan menerangkan tentang cara bagaimana proses kita menggunakan eksperimen heat transfer eksperimen. So daripada air ni akan mengalir kepada heater kita, dan daripada heater kita akan mengkaji hubungan antara between the distance of the heater and the temperature.
Okay. So
I'm going to show you the startup procedure for lab 2, which is radial heat transfer. Okay.
So
We turn on the heat to 50. Okay, after that we have to let the water boil.
Alright. Okay, after we take the value for 30 watts, we are going to set it to 40 watts.
Okay.
And then in a minute we can take the temperature readings. After we're done with 40 watts, we are going to turn it up to 50 watts. After we're done with 70 watts, we're going to set it to 90 watts. It's too hot?
Is it too hot?
Too hot.
hello, my name is Muhammad Faris bin AZHAR. I will represent our group results, different power for radiant heat conduction, where we use the experiment power at 30. We got a temperature 1, 43.5. For the temperature 2, we got 39.1. For temperature 3, we got 36.2. And temperature 4, we got 34.5. For temperature 5, we got 32.7. We run the result at power 30, 40, 50, 70, and 90. For our last experiment at power 90, we got a different temperature, where temperature 1 we got 73.4, at temperature 2 we got 63.4, at temperature 3 we got 56.6, at the temperature 4 we got over limit, which means TH means too hot, till temperature 7 we got too hot, which means the heat are over limit, we got 100 Celsius. For the radiant from temperature 1 we got 0, temperature 2 we got 0.01, for the temperature 3 we got 0.02, temperature 4 we got 0.03, temperature 5 we got 0.04, for temperature 6 we got 0.05, for temperature 7 we got 0.06.
Hello, my name is PATERUS, and today I'm gonna present the data analysis for our experiment that we have conducted on radial conductions. As you can see here, this is the chart that we have graph on temperature versus the distance from T1. So this is the temperature on the verticals, and the horizontal is the distance from T1 here. So each line represent the power. So for the light blue, it is for 30 watts, the orange is for 40 watts, and the gray is for 50 watts, the yellow is for 70 watts, and the dark blue is for 90 watts. So as we can see, there's a similarity for each line. The temperature for each line is gradually decreasing the further it is from T1. This is showing the relationship between the distance and the temperature for this experiment. And we can see here for the power of 70 watts and 90 watts. They stop here and here. This is showing there's a bit of an error while conducting the experiment. So we can conclude just from this data analysis that relationship between temperature and the distance is that the closer the closer it is to T1, the heater, the higher the temperature will be. That's all from me. Thank you.
Hi, my name is Wong. So I'll be talking about the discussion of radial conduction. So one of the set of the result we choose is 50 volts. So we have to use the equation in the theory section for with T1 to calculate T2. And we continue this way to find T3, T4, and all the others value for the thermocouples. So first we use 50 watt sets of data. So for T1 actually is 43 degrees. The material is copper. Thus the thermal conductivity is 388 watts. And the length between the size of the copper is 0.005 meter. So first at all, we use the equation given, which is T1 minus watts minus ln R2 divided by R1 and divide by 2 times pi times length times thermal conductivity, which is equals to T2. So T2 we use T1, which is 43 degree, minus 50 times ln 0.02 divided by 0.01 and divide 2 pi 0.005 and 388 equals to 38.95, which is the second temperature. So for the equation, we continue this way. So we can find T1 is 43, T2 38.95, T3 34.88, T4 30.802, T5 is 26.72, and lastly T6 is 22.63. So this is the graph we created. So for the blue one is experimental graph. As you can see, it's not going as linear. So for the theoretical graph, as you can see, it's going in a linear pathway. Thank you.
A very good day. So today I'm going to present on the discussion number 2 from the theoretical and experimental data differences. As shown above, the theoretical data's temperature decreases more than the experimental data. This is because of heat conduction error. The formula for estimating the heat conduction was derived under the condition that the fluid temperature is uniform. If we apply the formula, the heat conduction error will be underestimated. Error can be caused by environmental or surroundings as the temperature of the room affecting the heat transfer of the experiment. It can also be caused by fault of temperature sensor reading when heat is conducted along the temperature sensor body. The error can also be suggested by the unknown factors of experimental such as electrical composition, accuracy, and many more. And lastly is the conclusion. So there is 5 points. The first, the further the distance from the heat source, the lower the temperature due to the heat has been removed along the way of the container. Second, the more the power applied, the higher the temperature will conduct to the container. Third, thermal conductivity is inversely proportional with the temperature difference and length. Number 4, with the formula applied, we found that the next temperature is directly proportional with the power applied, and in radius out or radius in. By increasing the radius out, the temperature increases. By increasing the radius in, the temperature decreases. Some materials are better heat conductors than others. This experiment uses copper as the heat conductor, which has good thermal conductivity with the value of 388 watts per meter Kelvin. That is all from me. Thank you.